Hello students, welcome to the GATE Academy. We have been awarded as the fastest growing GATE institute in India, and also we have been awarded the best innovation in open and distance learning. Okay, so let's continue. Welcome everyone. For those of you who have already seen the previous lecture, that is, who are aware of what these gate booster sessions are, welcome back. So, as you might know, that last night I have already conducted a gate booster session, in which we have covered the basic thermodynamics, the questions related to basic thermodynamics. And those of you who are joining us currently, that is, who have joined us newly, let me tell you what gate booster session actually are. So in the next 2 to 3 hours, I am going to cover such questions which are particularly crafted by yours truly to give you the maximum exposure to the most important concepts and subjects of thermodynamics. Okay? So in the next 2 to 3 hours, I am going to cover such questions which are power packed. That is, they are going to give you the maximum number of concepts, the maximum amount of learning in minimum number of time and minimum number of question. So this is the whole concept of our gate score booster. That each of this question will teach you the maximum number of concepts possible. Okay? Okay. So let's see. In the previous session, that is in the session 1 of the basics and applied thermodynamics, we have covered such questions that dealt with the basics of the thermodynamics. That is the first law, second law, entropy, available energy, properties of pure substance. That is what we have covered. If you have not seen that video, then I highly recommend that after watching this video, please go back and watch that video, because that video contains some important concepts about the basic thermodynamics. If you have not watched that video, do not worry. This video is not going to be related. The questions that we are going to attempt now, these questions are not going to be connected with that question. Yeah, they are going to use the concepts of the basic thermodynamics, but I already assume that since you are preparing for your GATE exams, which is just a few weeks away, so you have already prepared, or you already are familiar with the concepts that we are going to use now. Okay? So, anyone there? Good morning. Good morning to you too. So let's start without further wasting your time. Let's start with the next question. Okay. Good morning to all of you. So let's start without further wastage of time. So the question is coming in front of you. This question is related to Rankine cycle, the modification of Rankine cycle, basically reheating and regeneration. As some of you was asking that this is an important concept. So let's go with this question. Okay. So the question is coming in front of you right now. Read the question. Read the question. Till that time, let me draw the important points and make note of the important data given in the question. So in this question, it will be beneficial if you can draw the plant diagram. That is, if you can draw the schematic diagram of the plant, I think it will be very beneficial for you. With further practice, you can work without drawing the diagram also. With further practice, you can solve the question without drawing the schematic diagram of the plant. But currently, for those of you who have not practiced much, I would recommend that at least practice with the basic schematic diagrams of the question. Okay, so let's see. Because in this question, the whole concept is about identifying which enthalpy is about which point. In this question, the whole concept is about identifying which enthalpy is related to which point. Okay. Okay, so I'm reading the question for you. In a modified Rankine cycle with reheating and regeneration. So in this cycle, there is both reheating and regeneration. Okay, the specific enthalpy at different points are given below. The specific enthalpy at different points are given below. Okay, at inlet of high pressure turbine and low pressure turbine, at outlet of high pressure and low pressure. So you can see that the enthalpies at different points are given in the question. What you need to do is identify which enthalpy is related to which point. Okay, and the other given data is the steam is blade at the outlet of high pressure turbine. Read the last line. If steam is blade at the outlet of high pressure turbine, calculate percentage of blade stem per kg of steam in cycle and efficiency of the cycle. Okay. I hope you have noted down the enthalpy data. I hope you have noted down the enthalpy data. If not, then take a screenshot because that will be very helpful. Okay. Okay. So let's see. So this is basically the schematic diagram of the whole plant. This is the schematic diagram of the whole plant. Okay. First, there is a high pressure turbine which is working in the high pressure ratio. Then from this turbine, some steam is bled out. See, in the question they have written, bringing the question up. In the question they have written that steam is bled at the outlet of high pressure turbine. Okay, so the steam has been bled at the outlet of high pressure turbine. I'm assuming that 1 kg per second of mass flow rate is the mass flow in the cycle. That is, the mass flow in the cycle is 1 kg per second, and out of that, let's say m kg per second is going into the regenerator. M kg per second is going into the regenerator, and this is called as the blade steam. This is called as the blade steam. Okay, and the rest of the steam that is 1 minus m kg per second, 1 minus m kg per second is going to the reheater to gain heat again. Okay, 1 minus m kg is going into the reheater. Some heat is again added to the reheater. Then there is a low pressure turbine. From the low pressure turbine, 1 minus m kg is coming into the condenser. 1 minus m kg is coming into the condenser. Then from condenser it is going to the low pressure feed pump. The low pressure feed pump will raise the pressure of this fluid to this intermediate pressure. The low pressure feed pump will raise the pressure of the fluid to this intermediate pressure. That is the pressure at the outlet of high pressure turbine and at the inlet of the low pressure turbine. Okay. So then this fluid is entering the regenerator along with the blade stem. This fluid, this condensate, is entering the regenerator along with the condensate. Okay, so finally m and 1 minus m kg per second is mixing in the regenerator. Some heat exchange is occurring in this regenerator, and then total 1 kg per second is going into another feed pump. Okay, this fluid is going into another feed pump, and then this feed pump is raising the pressure to the pressure of the inlet of the high pressure turbine. This feed pump will raise the pressure from this point to this point. Okay, this feed pump is going to raise the pressure from this to this. Okay, and then it is going to enter the boiler. Okay, so let me draw the TS diagram. That will be beneficial for you. Okay, so there is three pressure difference. There is three pressure difference that we are talking about here. See, one is this pressure. One is this pressure. That is the pressure at which the inlet of the high pressure turbine is. Then there is this second intermediate pressure. This intermediate pressure. This is the pressure at the exit of the high pressure turbine. This pressure is at the exit of the high pressure turbine where the blade stream is occurring. And the third pressure is the condenser pressure. The low pressure, the lowest pressure, that is the condenser pressure. So I can say this is the boiler pressure, this is the condenser pressure, and this is the intermediate pressure. This is the intermediate pressure. Okay, hopefully this much is clear to you. Hopefully this much is clear to you. Okay, so now let's see. Let's give some points. Let's just mark some points to it. Just randomly, let's mark some point. Let's call this as point 1. This is point 2. This is point 3. Let's call this as 4. Then this is 5. Let's call this 6. This is 7. And this is 8. Okay. The same point corresponding in the schematic dia. So let's see. This point will be 1. Then this is 2. So this point will be 3. Yeah. And this point will be 4. This is 5. This is 6. Then this will be 7. This will be 7. And this will be 8. Okay. Till this much, I hope everything is clear. I hope everything is clear up to this much. That this is the diagram, the schematic diagram of the plant. This is the schematic diagram of the plant. Good morning. So this is the schematic diagram of the plant. And this is the TS diagram. Okay. All the corresponding points have been matched. All the corresponding points have been matched. Let me reiterate what is happening here. So from 1 to 2, the steam is expanding in the high pressure turbine. 1 to 2, steam is expanding in the high pressure turbine. Then from 2 to 3, the steam is getting reheated. From 2 to 3, in the reheater, the steam is getting reheated from 2 to 3. Okay. Then from 3 to 4, the low pressure turbine. Adiabatic expansion in the low pressure turbine. 3 to 4. Then 4 to 5 is the condensation. 4 to 5 is the condensation. Okay. Then 5 to 6 is the pump work. That is low pressure feed pump. This pump work is 5 to 6. Okay. Now see what happens. At point 6, this fluid enters the regenerator. At point 6, this fluid enters the regenerator. Okay. And also from point 2, the blade steam, that is mkg per second, this blade steam, this is entering the regenerator. This blade steam is entering from point 2 into the regenerator. So what happens is the blade steam, that is the steam at 2, will condense. The steam at 2 will lose its heat and condense. The steam at point 2, that is mkg per second, this will lose the heat in itself. That is, it will lose the latent heat. This will lose the latent heat, and that latent heat will be gained by the fluid at this point. The latent heat will be gained by the liquid. The latent heat will be gained by the liquid at 6, and so the fluid, the hot fluid at point 2, that is the blade steam, the hot fluid or the blade steam will condensate. The blade steam will lose its latent heat and condensate, and this heat will be given to the cold fluid, that is the cold liquid at 6, and this cold liquid will rise in temperature. The cold fluid, the temperature of this cold fluid will rise from 6 to 7. Understanding what is happening? The hot fluid, that is this this blade steam is condensating from 2 to 7. This blade steam is condensating from 2 to 7, and this amount of heat that this has lost is gained by the liquid, at 6, and then this liquid temperature rises to 7. Okay, and at 7 the whole mixture is exiting from the regenerator. So at 7 the mixture is exiting from the regenerator and entering the high pressure pump. At 7, because this point is also 7 and this point is also 7. So at 7 the whole mixture is exiting from the regenerator and entering the high pressure pump. And then the pump work is from 7 to 8, and from 8 to 1 there is heat addition in the boiler. So I hope this much is clear. Okay, so now the enthalpy data are given in the question. Do one thing. Corresponding to this point, try to identify which enthalpy is which. That is, find the value of, what I am asking you to do is find the value of H1, H2, H3, H4, H5, H6, H7 and H8. Okay, this is what you have to do. This is what you have to do. Okay, note down this diagram. Note down this diagram. Either this or this, whatever you wish, whichever is convenient for you. Note down this diagram and then go back to the question. I will bring the question in front of you. Note this diagram. Then I'm going to bring back the question in front of you. And then from that data, collaborate with this one, that which point has which enthalpy. Okay, that is all that you must do. This is something that you have to do. Identify which point carries which enthalpy. Okay, so I hope you have noted down this. I hope you have noted down this. Okay, I hope you have noted it down. So now I am going to bring back the question. I am going to bring back the question. Okay, so the question is here. Okay, so relate that which enthalpy is related to which point. So let's see. Okay, so let's see which enthalpy, that is which point carries which enthalpy. Okay, so here, see this. Everyone is in the unit of kilojoule per kg. Each of this figure has a unit of kilojoule per kg. Okay, so check from this. Is this the data that you are getting? Is this the data that you are getting? Tell me, is this the data you are getting, or do you have any doubt? Is this the data that you are getting, or do you have any doubt? Tell me, because this is a very important process. Hello, anyone there? Anybody still awake? Say something. Sleeping is not going to help you. Tell me. So is this the data set that you are getting or not? Are you able to collaborate these points with the data they have given you? Are you? Or do you have any confusion in this part? Have you attempted this part? Have you attempted this part? That is collaborating the data they have given you in the question. Yeah, someone is saying something. If we understand the diagram, it will be okay. Yes, yes. If you understand the diagram, then it will be clear. Okay, so let's try to explain the diagram once more. What is happening? Let's try to explain the TS diagram. Okay, I am explaining the TS diagram. Collaborate with that schematic diagram. Okay, see what is happening. From 1 to 2 is the high pressure turbine. 1 to 2 adiabatic expansion is the high pressure turbine. This is the high pressure turbine. 1 is the inlet of the high pressure turbine and 2 is the outlet of the high pressure turbine. Okay. Then from 2 to 3 there is reheater. From 2 to 3 there is reheat. So the inlet of the reheat is at 2 and the outlet of the high pressure turbine is also at 2. Okay, the inlet of the reheater is at 2 and the outlet of the high pressure turbine is also at 2. So from 2 to 3 there is reheating. From 2 to 3 there is reheating. At point 3, that is the inlet of the low pressure turbine. This is the low pressure turbine because this turbine works in the low pressure region. This turbine works in the low pressure region. So from 2 to 3 is the low pressure turbine. Okay. So third point, that is point 3, is the inlet of the low pressure turbine. Third point is the inlet of the low pressure turbine. Good morning. Good morning. So third point, point 3, is the inlet of the low pressure turbine. Okay. Fourth point is the exit of the low pressure turbine. Fourth point is the exit of the low pressure turbine. So from 3 to 4 there is adiabatic expansion. From 3 to 4 there is adiabatic expansion in the low pressure turbine. Low pressure turbine because this is acting in the low pressure region, and this is called as high pressure turbine because this works in the high pressure region. Okay. Now next point. From 4 to 5 is the condensation. From 4 to 5 is the condensation. From 4 to 5 is the condensation. This is occurring in the condenser. 4 is the outlet of the low pressure turbine. 4 is the outlet of the low pressure turbine and the inlet of the condenser. Similarly, 5 is the outlet of the condenser. 5 is the outlet of the condenser and the inlet of the low pressure feed pump. This is the feed pump. This is the feed pump. This is the feed pump, and this is called as the low pressure feed pump because this feed pump works in the low pressure region. Okay, 5 to 6 is the work done in the low pressure feed pump, and this is called low pressure feed pump because it acts in the low pressure region. Okay, so 5 to 6 is the low pressure feed pump. 5 is the inlet to the low pressure and 6 is the outlet to the low pressure. Okay, now coming to the most important part, the regenerator. The regenerator. What happens in the regenerator? So understand this because this is very important. Okay, so understanding what happens in the regenerator is very important. So let's see. In the regenerator, the blade steam. Okay, in the regenerator, the blade steam from point 2. What is blade steam? What happens is that all the steam that has expanded in the high pressure turbine, is not carried forward for reheating. All the steam that has been expanded in the high pressure turbine is not carried forward for reheating. Some part of it is taken out. That is, let's say mkg per second is taken out, and that mkg is supplied to another heat exchanger called as the regenerator. Okay, some part is taken out and supplied to a regenerator. Okay, so what happens in the regenerator? This fluid is hot. So this fluid, when it comes in the regenerator, this fluid or this steam will lose its energy, will lose the latent heat and condense. So this fluid that is entering the regenerator, hot fluid, this will lose the latent heat and condense. So this fluid at 2, the blade steam, will lose its heat and condense and come to 0.7. Correct? This steam will lose its heat and condensate and come to 0.7. Okay, clear up to this much what is happening with this steam? Okay, now see. This steam that is this liquid water that is entering from the low pressure feed pump, this will mix with this hot temperature fluid. Okay, and as this hot fluid lose its latent heat, similarly this heat will be absorbed by the cold fluid. This heat will be absorbed by the cold fluid, and this cold liquid will see a rise in temperature. This cold fluid will face a rise in temperature and become saturated at 0.7. Okay, this cold fluid will gain the heat from the condensation of this hot fluid. This cold fluid will gain the heat and the temperature will rise up to 0.7. Bleeding regenerator meaning. Okay, see, what happens is bleeding means that you are taking some steam out of the turbine, you are taking some steam out of the turbine and then supplying it for doing other work. Okay, you are taking some steam from the turbine and then you are doing some other work. It is called as bleeding because similar to bleeding in humans, when we get a cut, some of our blood flows out, some of our blood flows out. Now this blood can be used for saving other lives also, or this may be completely wasted. So similarly in turbine, the bleeding means that some steam is taken out and the other steam carries forward. Okay. Now what happens in the regenerator? What happens in the regenerator? That this steam is getting condensate. This steam is going to condense. This steam is going to condense and come to point 0.7. This is the condensation of this blade steam. This is the condensation of the blade steam. This occurs like this. This is the condensation of the blade steam. Okay, from 2 to 7, the blade steam is condensating. And because of this condensation, the heat that it is losing, the heat that the blade steam is losing, that heat is used to heat up this cold fluid. The energy that this blade steam is losing, that energy is used to heat up this cold fluid, is used to heat up this cold fluid so that its temperature rises to 0.7, so that its temperature rises to 0.7. What is the use of it? The use is that since you are able to heat this fluid from 6 to 7 without any additional supply of heat, so the net heat that you are going to supply to the cycle is reduced. The net heat that you are going to supply to the cycle has been reduced. Why? Because this much heating is done without addition of any external heat. This much heating of the cold water is done without addition of any external heat. That's why we do the regeneration. That's why we do the regeneration. Yeah, okay, we will going to forward this. Don't worry, we are going to forward this, but this needs some explanation for some people. Some people needs some explaining with this. Okay, but anyway, let's finish this now. Hurry up. So now you see this data has been collaborated. This data has been collaborated according to that the given data in the question. These are the points and these are the enthalpies. Okay, so now the first question they have asked, and the first thing that you must do, is you need to calculate the percentage of the blade steam, and that is easy. All you need to do is apply energy balance on this regenerator. That is, the energy coming in is equal to energy going out. So let's see the energy that is coming in. So M mass flow rate is bringing energy H2. This is the energy coming in, plus from here 1 minus M kg per second is bringing energy of H6, and this is equal to the energy going out, that is 1 kg per second into H7. Okay, understanding how we have done this? The energy coming from 2 is the mass flow rate is M and it is bringing enthalpy of H2. From here 1 minus M and bringing the enthalpy H6, and at the outlet there is 1 kg and that is 1 kg at H7. So from this diagram you can get the value of M. From this equation you will get the percentage of the blade steam, and the percentage of the blade steam, that is M, is equal to 32%. Okay, clear up to this part? See, in this session, the question that we are going to do, they are particularly crafted by me. Okay, so these questions are not going to directly come in your GATE exam, but the concepts that you are going to learn from this question, they are definitely useful for your GATE exam. The concepts that you are going to learn from this question, they are going to be useful for your GATE exam. These questions have never come. As of this, questions have directly never come in your GATE, but parts of it or concepts of it have definitely come in your GATE exam. Okay, so let's see. Now we need to calculate the efficiency. Now we need to calculate the efficiency. Okay, so let's see how to calculate efficiency. So see, this is where there is a major chance of making a mistake. So watch carefully. Please note down this point that m kg per second is going out from here. So in this region only 1 minus m kg per second is flowing. Okay. In this region only 1 minus m kg per second is flowing. Okay. So now let's see how to calculate the efficiency. Neta is equal to work of the high pressure turbine plus work of the low pressure turbine minus work of the let's say low pressure pump minus work of the high pressure pump divided by, there is two heat addition. Note down this point, there is two heat addition. One is the Q added in the boiler, one is the Q added in the boiler plus the Q added in the reheater. Okay, so there is two heat addition. Okay, so this is how you are going to calculate the efficiency. One of the way is this, the other simpler way. Let me show you the other simpler way also. The other simpler way is this. Neta is equal to 1 minus Q rejected by Q added. Correct? This is the simple formula for efficiency. So now you can write it as 1 minus heat rejected. The heat is being rejected at this part. The heat is being rejected at this part. So heat rejected, please note that there is 1 minus m. 1 minus m kg is flowing in this part. So heat rejected is 1 minus m into H4 minus H5, and the heat added, that is the heat added in the boiler. The heat added in the boiler, that is in this part, 1 kg is flowing. 1 kg per second is flowing in this part. So the heat added in the boiler is H1 minus H8. And the heat added in the reheater, this is the reheater, and in this also some heat is added. So the heat added in the reheater, this is basically 1 minus m. Why? Because only 1 minus m is flowing from here. M is going in this direction, so only 1 minus m is getting reheated. So 1 minus m into H3 minus H2. Okay? So from this you can calculate the efficiency. From this you can calculate the efficiency. Ducts are basically in the fluid mechanics. The ducts numerical that you are talking about, they are basically dealt in fluid mechanics. Okay? So getting my point, this is how you calculate the efficiency. Please note that in this region, in whole of this region, only 1 minus m is flowing. Okay, so the heat rejected will be multiplied with 1 minus m. The heat added in the reheater will be also 1 minus m. Okay, clear up to this part? Again, if you are talking about this part, so let me make it clear. The work of the high pressure turbine, that is work of the high pressure turbine H, this will be the work of the high pressure turbine will be 1 into H1 minus H2. But the work of the low pressure turbine, that will be 1 minus m into H3 minus H4. H3 minus H4. Okay, so keep in mind. On power plant, how the numerical will come from power plant. Yesterday we have done a question. That is in the last session, we did a question in which there was data given. That is, data was given at 2 pressure. and then we had to find the different enthalpies, the dryness fraction. So from that also that question can come, and the other type of question is from the modification of the Rankine cycle that we are doing right now. The other type of question can come from the modification of the Rankine cycle that we are doing right now. Okay, so anyway, keep this in mind. Keep this in mind that the work of the low pressure turbine will be 1 minus m. Do not forget the part of 1 minus m. M is 32% or M you can write it as 0.32. Okay. Similarly, the work of the low pressure pump. The work of the low pressure pump, in this region only 1 minus M is flowing. In this region only 1 minus M is flowing. So this will come as 1 minus M into H6 minus H5. And similarly, the work of the high pressure pump, in this region 1 kg is flowing. M is coming from here, 1 minus M is coming from here, so total 1 kg. So in this region it will be 1 into H8 minus H7. Okay, so these are all the data that you need to know, and be very careful about this blade stream. Okay, yes, so let me see, the answer is 42.4%. Correct, the answer is 42.4. Okay, the answer is 42.4. So hopefully this is clear to you. Hopefully this is clear to you. This will be the simpler approach to calculate the efficiency. This will be the simpler approach to calculate efficiency. Now another modification that can be done with this question, another modification that could have been done with this question is they would have given you the power output. They would have given you the power output, and then they would have asked what is the actual mass flow rate in the cycle. Okay, what is the actual mass flow rate in the cycle? So you can calculate the specific work. This, the numerator is the specific work, that is the work per kg of fluid flowing in the cycle. This is the specific work, the work per kg of fluid flowing in the cycle. So when you have the specific work, the total work is basically mass flow rate into specific work. That is, the total work, it will be in kilowatt, is equal to mass flow rate into specific work. And this will be have a unit of kilojoule per kg. Okay, so this is the specific work, this is the total specific work. So when you substitute this here, and if they have given you the total work, then you could have calculated the mass flow rate. Sorry, let me represent with different symbol. Let's say this mass flow rate is capital M. Then you could have calculated the total mass flow rate in the cycle, or vice versa. If they have given you the total mass flow rate, you could have calculated the total work. Okay, so this is all the modification that they can do in the Rankine cycle. This along with the previous question that we have done in the previous session. Okay, so these are all the modification that they can do in the Rankine cycle. Yes, the efficiency is 42.4%. So let's move on to the next question. Okay, the next question is from Brayton cycle. So let me bring it up. Okay, so you can see the question in front of you. Let me note down the important data. Till then, note down that chart, that TS diagram they have given. Note it down. Okay, read the question. In the question, they have mentioned perfect intercooling and perfect reheating. Correct? They have mentioned something like this: perfect intercooling and perfect reheating. Tell me, what does that mean? What is perfect intercooling and what is perfect reheating? Tell me what that signifies. Yes, definitely. Perfect intercooling means T3 is equal to T1. And what does perfect reheating means? What does perfect reheating means? Dear Pramod, this session is not about solving the gate question. I'm sure you will find many videos in our website that has solved the previous year gate question, or you can also solve the previous year gate question solution from our books. But in this session, we are going to just revise the concept. This is not about solving gate question. This is about revising your concepts. Okay? Yeah. Perfect reheating means T5 is equal to T7. Okay? Perfect reheating means T5 is equal to T7. Okay? So let me draw the diagram. Okay, so let's see. So these are the points. This is 1, this is 2, this is 3, this is 4 dash, this is 5, this is again 6, here is 7, here it is 8 dash. Between here they have given a point 9 and somewhere here they have given a point 10. Okay, this pressure is 9 bar, this pressure is given as 3 bar, and this pressure is given as 1 bar. Correct? Okay. So as they have said that perfect reheating means T5 is equal to T7 and they have given the maximum temperature, so this becomes 1000 Kelvin. Okay. Then perfect intercooling means T1 is equal to T3 and this is the minimum temperature, so this means it is 300 Kelvin. Okay, this is the data they have given. Okay, also they have given the isentropic efficiency. So this efficiency is 0.8 and this efficiency is also 0.8. Okay, and effectiveness of the regenerator is zero point 0.9. Okay, so this is the data they have given. This is the data they have given. So now let's see how to do this question. How to do this question. But first, let me draw one more thing. The blue line represent the blue line that I have drawn right now. The blue line that I have drawn right now. These represent the ideal adiabatic process. Okay, that is the isentropic expansion. This 7 to 8. This represent the These represent the isentropic ideal expansion. Okay, so this is what should have been done, but because of the isentropic efficiency of the turbine and the pump, the real process is occurring something like this. The real process is occurring something like this. So your actual cycle, the cycle that you are going to consider is 1, 2, 3, 4 dash 10, 5, 6, 7, 8 dash 9 and 1. Okay, the real cycle is 1, 2, 3, 4 dash 10, 5, 6, 7, 8 dash 9 and 1. Okay, 4 and 8 are just the ideal concept. They are not part of your actual cycle. They are not part of your actual cycle. Okay, so let's see how to do this question. Let's see how to do this question. Okay, yeah, another important data they have given, that is gamma of air is equal to 1.4 and Cp they have given 1 kilojoule per kg Kelvin, it will be 1 kilojoule per kg Kelvin. Okay, so they have given you the Cp and they have given you the gamma. Okay, so let's see how to do this question. So now see, 1 to 2 is isentropic. 1 to 2 is an isentropic. In such question, it is always beneficial. In such question, it is always beneficial to find out the temperature at different points. Whenever such questions come related to Brayton cycle, it is very useful to find out all the temperatures given, because in some part of the question that will be helpful. Okay, so let's try that. So what we can say is T2 by T1 is equal to P2 by P1 raised to the power gamma minus 1 by gamma. Correct? Because 1 to 2 is an adiabatic, ideal adiabatic expansion. So adiabatic expansion holds this formula. Adiabatic expansions hold this formula, that is T2 by T1 is equal to P2 by P1 raised to the power gamma minus 1. So from this, when you will calculate, you will get T2 is equal to 400.6 Kelvin. Correct? Correct up to this part? Now see, we can talk about 4 and 3, because T4 divided by T3, T4 divided by T3 will be at the same pressure ratio. That is, this will be P, let's say P4 divided by P3 raised to the power gamma minus 1 by gamma. Gamma minus 1 by gamma. Backwork ratio will be 52.2. Yeah, so backwork ratio is 52.2%. Okay, anything else? Yeah, backwork ratio will be 52.2%. Okay, so let's see. From here we will get T4 will be the same as T2, that is 410.6 Kelvin. Okay, so this is T4. Okay, now we need to calculate 4 dash, because the actual cycle is occurring from 3 to 4 dash. How to do that? See, the isentropic efficiency of the pump is given. The isentropic efficiency of the pump is given. So neta of pump is nothing but the ideal work divided by the actual work. So the ideal work should have been H4 minus, okay, let's do this right away. H4 minus H3, and the real work is H4 dash minus H3. Correct? The ideal work is 3 to 4 and the real work is from 3 to 4 dash. 3 to 4 dash. And since for pump the real work is higher, the real work has a higher value. So for efficiency calculation, we take the ideal work divided by the real work. For turbine, it is just the opposite of this, just the reciprocal of this. Okay, so this can be written as Cp T4 minus T3 divided by Cp T4 dash minus T3. Okay, Cp will get cancelled, neta of the pump is given. So from this you will get T4 dash, from this you will get T4 dash is equal to 438.25 Kelvin. Okay, so now we have T4. Okay, let's not care about 10 right now. Let's not focus about 10 right now. We know T5, let's calculate T6. We know T5, let's calculate T6. Similarly, using the similar type of relation, T5 divided by T6 is equal to P5 divided by P6 raised to the power gamma minus 1 divided by gamma. The similar relation is going to hold here. Okay, the higher temperature by the lower temperature is equal to the higher pressure divided by the lower pressure into gamma minus 1 by gamma. Okay, so from this when you calculate, you will get T6. You will get T6 as 735.29 Kelvin. Okay, 735.29 Kelvin. Okay, again 7 has the same temperature, 1000. The pressure ratio remains the same, 3 to 1, 3 to 1. That is, this ratio is 9 by 3, which is 3, and this ratio is 3:1, which is 3. So 8 will have the same temperature as the 6. You can calculate this also to see this. That is, I'm writing the relation for this 2 point. I'm writing the relation for 7 and 8. 7 and 8. So let's see. So T7 divided by T8 is equal to P7 divided by P8 raised to the power gamma minus 1 by gamma. Okay, so from this you can see, from this when you substitute, you will again get the answer that T8 is equal to 735.29 Kelvin. Okay, clear up to this part? Okay, now see. So now we have calculated T8. Time to calculate 8 dash, because 8 is hypothetical point. 8 does not exist in the real cycle. 8 is a hypothetical point. What we need is 8 dash. What we need is 8 dash. So again, how to calculate that? Neta of the turbine, that is equal to the actual work, because in case of turbine the actual work is smaller. In case of turbine the actual work is smaller. So the actual work is given by T7 minus T8 dash, and the ideal work is given by T7 minus T8. Correct? This is the actual work. This is the actual work. CP T7 minus T8 dash. T7 minus T8 dash into CP. This is the actual work. And this is the ideal work. This is the ideal work. And whenever there is a deviation from the ideal, the loss is going to be faced by us. We have to face the loss. So when in case of turbine, because of deviation from the ideal, the actual work that we get is lesser. In case of turbine, because of deviation from the ideal, the actual work that we get is lesser. And in case of pump, because of the deviation from the ideal case, the work that we have to give, the actual work that we have to give to the pump is more than the ideal work. Understanding my point? In case of pump, we give the work, and if it is deviated from the ideal, we have to give more work than the theoretical one. And in case of turbine, we get less work than theoretical one. Okay, so in case of turbine the actual work is less, and in case of pump or compressor the theoretical work is less. Okay, and efficiency is always the lesser by greater. Efficiency is always lesser by greater. Efficiency cannot be 1 or greater than 1. Okay, so in this case, the isentropic efficiency of the turbine is defined as the real work divided by the maximum or ideal work. Okay, so all the temperatures are known. So from this you can get T8 dash is equal to 788.24 Kelvin. 0.24 Kelvin. Okay, now comes the last part. And the last information. The efficiency of the regenerator. Sorry, effectiveness of the regenerator. The effectiveness of the regenerator. So can you tell me between which part is the regenerator working? Can you tell me that between which part the regenerator is working? What is actually the regenerator doing? Can you tell me? Let me show you the diagram. Let me show you the plant diagram. Maybe that will be helpful. Okay. So this is the plant diagram. Okay. This is the diagram of the plant. You can see the regenerator here. So now tell me that what is the regenerator actually doing? What is the regenerator actually doing? Between which part is the regenerator working? Can you tell me? Between which part is the regenerator working? What is the regenerator actually doing? Tell me that. Between 4 and 5. Okay. But between 4 and 5, there is regenerator and the combustion chamber. The CC is for combustion chamber. The CC is for combustion chamber. So between 4 dash and 5, there is a regenerator and a combustion chamber. Think about it a little more. Think about it a little more. Yeah, now you are coming to the point. 6 to 7. Let's see. No, no, no. Between 6 to 7 is the reheater. Between 6 to 7 is the reheater. Between 6 to 7 is the reheater working. See, what is the regenerator? Where is the regenerator located? Between the combustion chamber and after the compressor, after the second compressor, after the high pressure compressor. So the regenerator is basically working between 4 dash to 10. Correct. The regenerator is working between 4 dash to 10. And again see that the second pipe that is coming into the regenerator, there is another second pipe that is coming into the regenerator, that is entering after the second turbine. After the second turbine. So that means from 8 dash to 9. Okay. So what it is doing, first let me identify which is the fluid that is entering. The first point, the cold fluid is entering at 4 dash and leaving at 10. In first regenerator, and that is in the regenerator, the cold fluid is entering at 4 dash and leaving at 10. And the hot fluid that is coming from the turbine, the hot fluid coming from the turbine, that is entering the regenerator at 8 dash and leaving at 9. That is entering the regenerator at 8 dash and leaving at 9. And that is why the point 10 and 9 are given. That is the reason why point 10 and 9 are given. So now let me tell you what the regenerator actually does. Now let me tell you what the regenerator between 6 to 7 is the reheating. Between 6 to 7 is the reheating. Okay. So let me now tell you what the regenerator actually does. See, the hot fluid enters the regenerator. Perhaps I should draw this part. See now. See what's happened. In the regenerator, the hot fluid is entering at 8 dash. It is getting cooled and leaving at 9. Okay, this is the hot fluid. This is the hot fluid. Or hot air, whatever you want to call it, because this is basically air. And the cold air is entering at 4 dash. The cold air is entering at 4 dash and leaving at 10. The cold air is entering at 4 dash and leaving at 10. This is cold air. Clear up to this part? Clear up to this part? The hot air is losing the heat and is cooled from 8 dash to 9. From 8 dash to 9. The temperature is reduced for the hot air. And the cold air is getting heated from 4 dash to 10. 4 dash to 10, the cold air is getting heated. So heat is extracted from the high temperature fluid and given to the cold air. Given to the cold fluid. Okay. Clear up to this part? Clear up to this part? Okay. So now see what is the effectiveness of the regenerator. Now let me tell you what is the effectiveness of the regenerator. Okay. So as I was saying that in the regenerator, the hot fluid, the hot air is entering from 8 dash and getting cooled to 9. That is 8 dash is the high temperature of the hot fluid and it is getting cooled to 9. 8 dash is the high temperature of the hot air and it is cooled to 9. And this heat is given to the cold air. This heat is given to cold air. So the cold air that is entering from 4 dash is getting heated to 10. The cold air that is entering at 4 dash is getting heated to 10. From 4 dash to 10. From 4 dash to 10. So the high temperature air is losing heat and the cold temperature air is gaining heat. So it is losing heat, so temperature is reduced from 8 dash to 9. This is gaining heat, so temperature is increased from 4 dash to 10. This is what the regenerator does. This is what the regenerator does. Now comes the effectiveness of regenerator. So effectiveness is basically how effectively it can heat up the cold fluid. Okay, so let's see that. The effectiveness of the regenerator, the effectiveness of the regenerator, that is effectiveness of the regenerator, it is defined as how much is the temperature change of the cold fluid, that how much is the temperature change of the cold fluid. So basically T10 minus T4 dash. This is the temperature change of the cold fluid divided by the maximum possible temperature change of the cold fluid, the maximum rise in temperature of the cold fluid. And see, the cold fluid is entering at 4 dash, correct? The cold fluid is entering at 4 dash. The maximum rise that the cold fluid can see is when its temperature will rise from 4 dash to 8 dash, correct? Because 8 dash is the maximum temperature, 8 dash is the maximum temperature, and 4 dash is the minimum temperature that this regenerator is facing. 8 dash is the maximum temperature and 4 dash is the minimum temperature that this regenerator is facing. Okay, so the maximum rise in temperature, of the cold fluid can be from 4 dash to 8 dash, because further rise is not possible. Further rise is not possible. So the maximum temperature rise that the cold fluid can experience is from 4 dash to 8 dash. Okay, this is the minimum temperature and this is the maximum temperature, and this rise, that is T8 dash minus T4 dash, is the maximum rise in temperature that the cold fluid can experience. Okay, this is the maximum rise in temperature that the cold fluid can experience. Okay, so all of this data is known except T10. All of the data are known except T10. So from this you can calculate T10. This will come out to be 753.24 Kelvin. Okay, T10 is 753.24 Kelvin. Okay, so this is the T10. Okay, so now see, I think every data is known. Also you can calculate T9 also. You can also calculate T9, because this will be the same as the temperature fall of the hot fluid, that is T8 dash minus T9 divided by the maximum temperature fall, which will be 8 dash minus T4 dash. Okay, this can be said in both the way, either the temperature rise of the cold fluid or the temperature drop of the hot fluid divided by the maximum change in temperature, that is possible. Okay, temperature rise of the cold or temperature drop of the hot divided by the maximum change in temperature. Okay, so this is how you find out the effectiveness of the regenerator. Okay, so from this you can calculate T9 also, but that is not necessary. Calculating the T9 is not necessary. But anyway, let's see. So now the question asks the back work ratio. What is the back work ratio? Earlier we have studied the work ratio. Now tell me, what is the back work ratio? Tell me that. In previous questions we have studied the work ratio. Now tell me, what is the back work ratio? Type. Give your answer. What is the back work ratio? Compressor work divided by turbine work. Yes, the back work ratio is the compressor work divided by the turbine work. Okay, so please note that there are two compressors. And there are two turbines. So back work ratio is the compressor work. So the first work is occurring from T4 dash minus T3 plus T2 minus T1 divided by the turbine work. The turbine work occurs from T5 minus T6 plus T7 minus T8 dash. Note this that we are not going to deal with T4 or T8. T4 and T8 are just hypothetical concepts that do not exist in the real cycle. Yes, compressor work by work of the turbine. Please note a point that 4 and 8 are hypothetical points that do not exist in the real cycle. We have just used them for calculation, nothing else. They do not exist in the real cycle. So this is the back work ratio, and back work ratio will come as 52.2%. The back work ratio. Good morning. Good morning, Agarwal Sahab. So back work ratio will come as 52.2%. The back work ratio will come as 52.2%. Okay. Now the last part, the efficiency. So the efficiency is simply the total work divided by the heat added. And make a note of it, the heat is added first in this part. This is where the heat is added, Q addition. And second heat is added in this part, Q reheat. So there are two heat addition. The first heat addition is occurring from 10 to 5 and the second heat addition is occurring from 6 to 7. Okay, make a note of it. The work output is definitely from 5 to 6 and 7 to 8. Okay, so let me write them down. The efficiency, thermal efficiency is the total work. So the total work is T5 minus T6 plus T7 minus T8 dash divided by the heat addition. The heat addition occurs from T5 minus T10 plus there is a reheat also. In reheat also some heat addition occurs. In reheat some heat addition occurs. So that is T7 minus T6. Do not forget this part. Do not forget the heat addition in the reheat. Okay. Do not forget this part. So from this when you will calculate, you will get this efficiency is 44.5%. 44.5%. 44.5%. Okay. Now one interesting thing that I should make a note here, that you should make a note here, is see, when you do regeneration for a Brayton cycle, this is the Brayton cycle. When you do regeneration in Brayton cycle, the efficiency of the Brayton cycle increases. Of course, the efficiency of the Brayton cycle is increasing, and that is because earlier this much heat was going to be wasted. But now what happens is this heat is being supplied to heat this fluid. Okay, so the net heat addition has decreased. Correct. That is if we are not doing the reheating, that is the cycle. Consider a Brayton cycle with only regeneration. And without this reheating. So in that case what happens is, because of the regeneration, the efficiency increases. Okay, because of regeneration the efficiency increases, but the work output is not changed. For Brayton cycle with regeneration only, the efficiency increases but the work output is not altered. But in case of Rankine cycle with regeneration, the efficiency increases but the work output also decreases. Correct. Any doubt in this point? In Rankine cycle with regeneration, the efficiency is increasing. The efficiency increases because the heat supplied is reduced, and moreover the mean temperature of heat addition increases. For Rankine cycle with regeneration, the mean temperature of heat addition increases, so the efficiency increases. But for Rankine cycle with regeneration, the output work decreases. decreases. But in case of Brayton cycle, regeneration increases the efficiency without affecting the work. Understanding or not? Understanding this point or not? Let me rub this part. See, let me illustrate this. In case of Rankine cycle, this is the TS diagram. Whenever there is regeneration, this is the regeneration. Let's say some M mass is flowing for regeneration, then what carries on is 1 minus M, correct? What carries on is 1 minus M. Here is 1 minus M. Okay. Now the heat addition occurs in only this part. The heat addition occurs in only this part. And the heat addition occurs at a higher temperature. The heat addition occurs at a higher temperature. In Rankine cycle, because of regeneration, the heat addition is less and occurring at a higher temperature. So when the mean temperature of heat addition increases in Rankine cycle, efficiency definitely increases. Efficiency definitely increases. But what happens is the total work output, let's say this is 2 and this is 3, the total work output will be from now, the total work output, H1 minus H2 plus 1 minus M H2 minus H3. And without the regeneration, this is the work with regeneration. And without regeneration, the work output is H1 minus H2 plus 1 into H2 minus H3. Okay, so you can definitely see that in Rankine cycle, without regeneration, the work is more. With regeneration, the work is less, but with regeneration, the efficiency is more. Without regeneration, the efficiency is less. This is true for Rankine cycle with regeneration. In case of reheating, with the Rankine cycle, we cannot say if the efficiency will increase or not. In case of reheating with Rankine cycle, we cannot say the efficiency will increase or not, but we can definitely say the work output will increase. The work output will increase, that we can definitely say. Now let's see for the Brayton cycle. Now let's see for the Brayton cycle. Let's say this is where the regenerator works. This is where the regenerator works. And now the heat addition is only occurring between 5 to 1. Now the heat addition is occurring only between 5 and 1. So you can see the work output. The work output is given by H1 minus H2 minus H4 minus H3. And this is not going to change no matter if there is regeneration or not. Because regeneration is going to affect the heat added and the heat rejected only. The regeneration is going to affect the heat added and the heat rejected only. So work is not going to be affected by the regeneration. But if there is regeneration, then Q added is less. If there is heat at this, sorry, if there is regeneration from 4 to 5, then the heat addition is only from 5 to 1. Without regeneration, the heat addition will be from 4 to 1. Okay, understanding my point? So with regeneration, the efficiency of the Brayton cycle increases without affecting the work output. With regeneration, the efficiency is increasing because the heat addition is decreasing and the work output stays the same. So with regeneration is in Brayton cycle, the efficiency increases without reducing the work output. See, when I say work output, I means the work done by the turbine minus the work of the pump. That is the net work output. Whenever I say work output, I mean the net work output, turbine minus pump. In this case, in Brayton, it is more accurate to say compressor. This is not a pump, this is a compressor. Okay, just a technical accuracy. Okay, till this much is clear? This much is clear? Another point that I wanted to highlight for Brayton cycle is intercooling. Another point that I wanted to highlight was intercooling. See, what happens is, so this is 1, 2, 3, 4, 5, 6. See, when there is intercooling, this is the intercooling part. That is between 4 to 5, there is intercooling. When there is intercooling, the pump or compressor work is reduced. Correct? When there is intercooling, the compressor work is getting reduced. In case of intercooling, the compressor work is getting reduced. Because why? Because these are isobaric lines. These lines, that is these lines, they represent constant pressure lines and they converge on the left hand side. These isobaric lines, they converge on the left hand side. So in this part, the temperature range, if I have to say the temperature range between this, that means, let's compare this with this also. Let's say this is 4 and 5 dash. So the temperature difference in this part, that is T6 minus T5, is less than T5 dash minus T4. This is what I wanted to say. Okay, the temperature range in this part is less than the temperature change in this part. And you know the compressor work for Brayton cycle depends on the temperature range. Okay, so since this temperature range is less, so because of intercooling, the work of the compressor decreases. So net work output increases. Correct? Because of intercooling or multi-stage compression with intercooling, the work output increases, the net work output increases because the work input in the compressor, the total work input in the compressor, that is decreasing. Okay, clear up to this part? Okay, so that's all. Let's continue with the further question. Let's continue with the next question. The question is coming in front of you right now. Here. This is basically a vapor compression refrigeration cycle. Okay, so let's see. Now I think you know what does superheating means. Tell me, what do you mean by subcooling? Yeah, effect of reheating on Brayton cycle. Work output will increase. Effect of reheating is the work output will increase, but the efficiency of both the combined cycle is going to be decreased. With reheating, the work output is definitely going to increase, but the efficiency is going to decrease. That is because in the second part, the pressure ratio decreases. the second turbine works at a low pressure ratio. And that is why even though the net work output is increasing, the efficiency will decrease. The efficiency because of reheating will decrease, but the net work output will increase. This much I can say confirm about the Brayton cycle, but in case of Rankine cycle, there is no way to know if reheating will increase or decrease or have constant efficiency. That depends on the case. In case of Rankine cycle, reheating can have variable effect, but in case of Brayton cycle, reheating will always increase the work but decrease the efficiency. See, whenever we talk about saturated temperature, that is only in the case of Rankine cycle. In Brayton cycle, we always work with air. So there is no saturation liquid temperatures. Okay, so this is the question. Oh, so you are telling me subcooling. Yes, yes, yes. Subcooling is correct. When the temperature is less than the saturated liquid temperature. Yes, Agarwalji. That is correct. The subcooling is defined as when the temperature of the liquid is less than the saturation temperature of the liquid. Okay. So let's see how to do this question. Let's see how to do this question. Okay, so let's see. So in this case, there is superheating also at the inlet of the compressor, and there is some subcooling also. Okay, so the cycle is going to look like this. The cycle is going to look like this. Let's say this is 1, this is 2, this is 3, this is 4. Let's name this as 3 dash and let's call this as 2 dash. Okay, let's call this point also 1 dash, just for convenience. Okay, clear to this part? Now let's see. Interesting point is that, can you tell me what is the effect of subcooling? What will be the effect of subcooling? What will be the effect of subcooling on the refrigeration effect? What will be the effect of subcooling on refrigeration effect? What will be the effect of subcooling on refrigeration effect? That is cooling effect. Any idea? The effect of subcooling on the refrigeration effect. Type. Okay, see. If there was no subcooling, then throttling would have been done from 3 dash only. And we have come up to some this point. Okay. If there was no subcooling, then throttling would have been done from 3 dash and we have come to some this point. Okay. So in this case, when there is no subcooling, the refrigeration effect is only this much. Okay. In this case, when there is no subcooling, the refrigeration effect is only this much. But with subcooling, the refrigeration effect is this much. Okay, with subcooling, the refrigeration effect is from 4 to 1 dash. So you can clearly see that subcooling is going to increase the cooling effect. The subcooling is going to increase the cooling effect. Okay, clear up to this? The subcooling is going to increase the cooling effect. Another important point, another beautiful point is subcooling is also going to increase the heating effect. Correct. If this is used as a heat pump, then in that case, subcooling is going to increase the heating effect. How? Without subcooling, the heat that would have been rejected, was from 2 to 3 dash. Without subcooling, the heat rejected is 2 to 3 dash. With subcooling, the heat rejected is from 2 to 3. And you can clearly see that from 2 to 3, more heat is rejected to the higher temperature. So subcooling will also increase the heating effect. Okay. So subcooling increases the heating effect, it also increases the cooling effect. Okay, interesting point. Yeah, superheating. Superheating is definitely going to increase the work output. If you want to know that superheating is definitely going to increase the work output, but we prefer superheating because it ensures that no amount of liquid can ever enter the compressor. The benefit of the superheating is it ensures that no amount of liquid can enter into the compressor, and that's why the compressor stays safe. And also because of this superheating, the refrigeration effect increases. Because of superheating, the additional heating is done from 1 dash to 1. Additional heating is done from 1 dash to 1. So because of this superheating, the refrigeration effect also increases, and the work output or the work input into the compressor also increases, and the life of the compressor increases. That's why we always prefer a small degree of superheating. We always prefer a small degree of superheating. Okay, so let's see now. So there are two pressures. This is 7.5 bar, sorry, 7.4 bar, and this pressure is 2 bar. The temperatures are given as, this temperature is minus 10 degrees Celsius, and this temperature is given as 30 degrees Celsius, the saturation temperature. Okay, so now I hope you remember that how we used to calculate the enthalpy and entropy of the superheated steam. Do you? How to calculate the enthalpy and entropy of the superheated steam? So let's see that. Let's see how to do that. So let's see. H1 is going to be more than H1 dash, correct? H1, the enthalpy at 1 is going to be more than H1 dash. So H1 is equal to H1 dash plus Cp of the vapor into T1 minus T1 dash. T1 minus T1 dash. This is basically the increase in enthalpy of an ideal gas, because the superheated vapor is considered as an ideal gas. So this is the formula for increase of enthalpy of an ideal gas. Okay, H1 dash you can take from the chart. H1 dash you can take from the chart. Basically H1 dash is nothing but Hg at 7.4 bar. Okay, so H1 dash is Hg at 7.4 bar. Hg at 7.4 bar, that is 199.475. 199.475. Okay, so from this when you will substitute, you will get H1 will come as 190.658. This is H1. Okay, clear up to this? Now let's see how to calculate S1. That is S small s, S1. Okay, entropy at point 1, entropy at point 1 entropy at point 1 is going to be more than the entropy at 1 dash. Entropy at point 1 is going to be more than entropy at 1 dash. So this is basically given as S1 dash plus Cp vapor into ln of T1 divided by T1 dash. T1 divided by T1 dash. Okay, T1 dash is minus 10. T1 dash is minus 10, and it has been given in the question there is 5 degree of superheat. So T1, that is temperature at this, is minus 5 degrees Celsius. Okay, this you can know that this is equal to T1 is equal to minus 5 degrees Celsius, because there is 5 degree of superheat. So from this you can substitute the value. And you will get S1 is equal to 0.73. S1 is going to be 0.73. Okay, just substitute this data, this data. I'm putting on the data right now. So S1 dash that I was talking about, S1 is basically SG at 7 point, sorry, it is at 2 bar. Yeah, SG at 2 bar. S1 S1 is S1 dash, sorry, S1 dash is basically the SG at 2 bar. SG at 2 bar. Okay, so coming back, so this is how you get the answer. Now see, 1 to 2 is an adiabatic expansion, correct? 1 to 2 is an isentropic adiabatic expansion. 1 to 2 is an isentropic adiabatic expansion. So, can I say that S1 is going to be S2? Can I say this? Yes, I can. S1 is going to be S2 and this value will be the same as 0.73. Using the similar kind of relation, I can say S2 is equal to S2 dash plus CPV ln of T2 divided by T2 dash. Okay, I know the value of S2. I need to know the value of S2 dash. CPV is given in the question. T2 dash is 30 degrees Celsius. T2 dash is 30 degrees Celsius converted into Kelvin, and S2 dash is nothing but the SG at 7.4 bar. So check from here. SG, that is value of S2 dash is basically SG at 7.4 bar. So SG at 7.4 bar. Okay, that is 0.6848. SG at 7.4 bar is 0.6848. Okay, so when you substitute that data, you'll get the answer as, this will come to be, that is T2. T2 is going to come as 312.14 Kelvin. Okay, every other data is known. The only thing that you needed was, that is in this case, S2 dash is known from the table, CPV is given, T2 dash is 30 degrees Celsius. So T2 you can calculate from here. Okay, so why did we need a T2? Any idea? Why did we need a T2? We needed T2, the temperature at this point, to calculate the enthalpy at this point. We needed T2, that is the temperature at this point, to calculate the enthalpy at this point. So let's see how to do that. H2 is basically H2 dash plus CPV into T2 minus T2 dash. Okay, similar to this formula. Okay, so now just substitute. Yes, to find enthalpy. So now just substitute, bringing the table now. Now I am not going to tell you that which data you need at which pressure. That is what you have to do now. That which data from the table do you need for which point. Okay, you have to find H2 and you need to know H2 dash. Okay, so substitute the data and you will get the answer, that is H2 is going to come as 213.3774. Okay, this is H2. Okay, correct? Okay, so now tell me about this 2 point. Is the enthalpy at 3 dash higher or at enthalpy at 3? Which point has a higher enthalpy, 3 dash or 3? Which point has a higher enthalpy? 3 dash. Yes, the 3 dash has a higher enthalpy. So just apply the formula. H3 dash is equal to H3 plus Cp of the liquid into T3 dash minus T3. Correct? T3 dash is 30 degrees Celsius and T3 is 20 degrees Celsius because they have said there is 10 degree of subcooling. Correct? In the question they have said there is 10 degree of subcooling. So if 3 dash is at 30, then 3 is at 20 degrees Celsius. Okay? And of course 3 dash has a higher enthalpy. So H3 plus Cp liquid, because this is occurring at a constant pressure. So Cp liquid into T3 dash minus T3. So from this when you calculate, you will get H3 dash is equal to, H3 dash is already known. H3 will come as 45.939 kilojoule per kg. The units are kilojoule per kg. 45.939 is the value of H3. Okay? And of course, H3 is the same as H4. H3 is equal to H4. Why? Because this throttling is an isoenthalpic process. So H3 is going to be equal to H4. Okay? So now we have the value of H4 also, that is 45.939. Okay? So now the last part, refrigeration effect. They have asked in the question, calculate the capacity of refrigerator in tons of refrigeration and COP of the cycle. COP of the cycle if it is used as a heat pump. Okay? So let's see. The refrigeration effect is basically mass flow rate. Don't forget this, the mass flow rate into H1 minus H4. Okay? The refrigeration effect will be the mass flow rate into H1 minus H4. The mass flow rate is given in the question, I assume. Yeah, the mass flow rate is given in the question, that is 1.2 kg per second. Thank you. I am happy that you are finding this session as useful. Okay, so as I was saying, that the mass flow rate is 1.2 kg, that is given in the question. Don't forget that. So this is the refrigeration effect, but the unit will be in kilowatt. This has a unit of kilowatt. You don't have to give the answer in kilowatt. You are not asked to give your answer in kilowatt. What you have to do is give your answer in ton of refrigeration. You have to give your answer in ton of refrigeration. And refrigeration effect in TR, that is ton of refrigeration, is equal to H1 minus H4 divided by 3.5. Because 1 ton of refrigeration is equal to 3.5 kilowatt. Yes, so the answer will be 49.61 TR. Yeah, 49.4 is acceptable. COP is, yeah, that is where you have made a mistake. I'm sorry to say that, but COP you have made a mistake. See, what they have asked, the COP of the cycle if it is used as a heat pump. Read the question carefully, my dear. COP of the cycle, yes, the answer for the refrigeration effect is correct. The refrigeration effect, let me write it down, this will come as 49.6 ton of refrigeration. 49.6 ton of refrigeration. 49.4 is also acceptable. Now comes the COP part. Okay, so make a note of it that in the question, read the last line. In the question, they have asked COP of the cycle if it is used as a heat pump. And for a heat pump, the desired effect is the heat rejection at high temperature. And the heat rejection at the higher temperature is from 2 to 3. The heat rejection at the higher temperature is from 2 to 3. Okay. So the COP, let me write it down somewhere. The COP of the heat pump is equal to the desired effect, that is the heat generation, heat rejection at the higher temperature. So H2 minus H3 divided by the work input. So H2 minus H1. This is the COP. And yes, this will come as 7.37. This will come as 7.37. Okay. And of course, another thing, another interesting point, very interesting point, is this relation. COP of the heat pump is equal to 1 plus COP of the refrigerator. This relation will still hold. Check for yourself. Check for yourself. This relation will still hold. Even though vapor compression refrigeration cycle is an irreversible cycle, because throttling is an irreversible process. Okay, throttling is a irreversible process. You can see that throttling is an irreversible process. Throttling is an irreversible process. Yeah, that is the mistake that you have made. You did not read the heat pump. See, throttling is an irreversible effect. Throttling is an irreversible process. So because of that, the whole cycle is irreversible. Because of that, the whole cycle is an irreversible cycle. Unlike other cycles that you have studied till now, the vapor compression refrigeration cycle is an irreversible cycle, non-ideal irreversible cycle. But still, this relationship holds. This relationship holds. So this relationship, that is COP of heat pump is equal to 1 plus COP of refrigerator, this relationship is valid for refrigerator and heat pumps no matter they are reversible or not. Correct? This relationship is valid no matter if the heat pump is reversible or not. This relationship is always valid. Okay? Understood my point? Then now let's move to the next question. I think, yeah, let's move to the next question. So the next question is coming in front of you right now. Okay, see. For a diesel engine sucking in 80 cc of air, read the question first, I will read it later. Read the question first, I will read it later. Okay, so the question says that for a diesel engine sucking in 80 cc of air at 1 bar and 27 degrees Celsius, the clearance volume is 14.28% of swept volume. Okay, so they have given a relationship between the clearance volume and the swept volume. The expansion ratio is 1.6. Now tell me, what is expansion ratio? What is expansion ratio? Calculate the thermal efficiency of the cycle and also calculate mean effective pressure of the cycle. So you have to calculate thermal efficiency and mean effective pressure. So let's see how to do that. See, let's draw the cycle diagram first. This is a diesel cycle, so it will look something like this, like a macaroni. That's how I remember it. The diesel cycle looks like a macaroni. this is P, this is V, and they have given that in the question they have given that the engine is sucking 80 cc of air. 80 cc of air. Okay, so this V1 is 80 cc, 80 cubic centimeter. Okay, this is the data they have given. Any other data? Air at 1 bar and 27 degrees Celsius. So at this point, this is 1 bar and 300 Kelvin. Okay, this much data they have given. Okay, 80 cc of air at 1 bar. Okay, the clearance volume is 14.28% of the swept volume. Okay, expansion ratio V4 by V3, correct. Expansion ratio is that V4 by V3. Okay, so now they are saying the swept volume. The swept volume, that is, let's say V stroke or swept. The stroke volume, also known as the swept volume, this is nothing but V1 minus V2. That is, this is V2. Not writing it here, just this is the swept volume. So what they have said, the clearance volume, that is the V clearance, this is the minimum volume, and this is equal to V2. Okay, the clearance volume is basically V2. So what they are saying, that the clearance volume, that is V2, is equal to 14.28 divided by 100%. Yeah, that is percent of the swept volume, V1 minus V2. Okay, so we know V1, from this relationship, we can calculate V2. From this relationship we can calculate V2, and I think V2 will come as 10 cc. If I remember correctly, yeah, V2 will come as 10 cc, 10 cubic centimeter, 10 cc. Okay, now they have said the expansion ratio is 1.6, correct? The expansion ratio is 1.6, and the expansion ratio is V4 divided by V3. That is, RE, expansion ratio, is equal to V4 divided by V3. Also, V4 is equal to V1. V4 is equal to V1. So I can write it as V1 by V3. And this is given as 1.6. V1 is 80 cc. So from this we can know that V3 will come as 50 cc. 50 cc. So this is 50 cc. 50 cc. Correct? We have the information of all the main volume. We have the information. Yeah, that relationship is also valid. 80 cc level 1. No, 80 cc is not the 80 is the C. For a diesel engine sucking in 80 cc of air at 1 bar and 27 degrees Celsius. So they have said that the 80 cc is the total volume of the air that they have sucked in at 1 bar and 27 degrees Celsius. Okay, so 80 cc is the volume of the air that is at the suction stroke. That is, at point 1, the volume of the air is 80 cc. That is what they have said. Okay, 80 cc is the volume of the air that they have sucked in. Okay, 80 cc is the volume of the air that they have sucked in at 1 bar and 30 degrees Celsius. Okay, it does not mean the stroke volume. Okay, so let's see. So this was clear. Now let's see. Yeah, efficiency of the diesel. This is 1 minus 1 by R raised to the power gamma minus 1 into 1 by gamma into RC gamma minus 1 divided by RC minus 1. Okay, this is the efficiency of the diesel engine. Okay, so we know this R is called as the compression ratio. This R is known as the compression ratio. So R is basically nothing but V1 divided by V2. V1 and V2, both of this data are known. RC is the cutoff ratio. RC is the cutoff ratio, and that is V3 divided by V2. V3 divided by V2, that is the cutoff ratio. So R can be calculated, RC can be calculated. Just substitute in this equation, and you will get that this efficiency, that is the efficiency, will come out to be as 33.78 percentage. 33.78%. 33.78% is the efficiency. Okay, clear up to this? Clear up to this? Now let's see how to proceed further. The next step is to calculate the mean effective pressure. Okay, the next step is to calculate, yes, it is 33 is also acceptable. The next step is to calculate the mean effective pressure. To do that, we need two things: the swept volume and the work. We need to know the swept volume, that is already known. The swept volume is already known. Next thing that we need to know is the work. Done. The work done by the cycle. Okay. So let's see how to do that. Let's take the simpler approach about how to do that. Instead of calculating the work in each of the four processes, or the area under the diagram, there is a simpler way to calculate. See, we know the efficiency. So if we multiply efficiency with the Q added, then we will get the work of the cycle. Correct? We know the efficiency. If we multiply it with the heat added, then we'll get the work of the cycle. And heat is only added in one process. So instead of calculating work for all the four processes, we can simply do it here. Correct? We can simply do it by multiplying efficiency into Q added, and heat is addition in only one process. Okay? So let's see. For calculating this heat addition, I will need, let me write it down, Q added. For calculating the heat addition, I need to know the mass into Cp, because heat addition is at constant pressure, into T3 minus T2. Okay, so I need all of this data. Cp is given in the question, but I need to know the mass, T3 and T2. So let's calculate these. How to calculate this? Let's see. So 1 to 2 is an adiabatic process. So adiabatic process hold the relation T2 by T1 is equal to V1 by V2 raised to the power gamma minus 1. Correct or not? T2 by T1 is equal to V1 by V2 raised to the power gamma minus 1. Correct? So from this we can get T2. And T2 will come as 689.21 Kelvin. Okay. Now see the second point. From 2 to 3 is an isobaric process. So in isobaric process, I can write T2 by T3. Since the pressure is constant, so this will be V2 by V3. Correct? Since the pressure is constant, the temperatures are in the ratio of the volume. Okay? So V2, V3 are known, T2 is known. So from this, when you calculate T3, you can get as let's see. Yeah, T3 will be 309 Kelvin. So 3446.09 Kelvin. This is the value of T3. Correct? No problem up to this part. Okay. So now see. The second thing is the mass. We have calculated T3, we have calculated T2. Now we need to know the mass. How to calculate the mass? Process 2 to 3 is constant pressure, so work. Yes, that can be done. That can be done. You can calculate the total work. No problem with that. But I am saying that there is a simple way. You have already calculated the efficiency. Just multiply it with Q added. Just multiply with the heat added and you will get the work of the cycle. Correct or not? You will get the net work of the cycle just by multiplying the Q added into efficiency. So let's do that. But this is also correct. You can calculate the total work. No problem with that. You can calculate the total work. You have to calculate the work in this adiabatic process, in this adiabatic process, and this isobaric process. You can do that. No problem. But I think this will be an easier approach. Now you just need to calculate the mass. Now you need to calculate the mass. How can you calculate the mass? Any idea? Yes, exactly. Using the PV equal to MRT equation at point 1. So P1 V1 is equal to MRT1. Okay, M will be constant for the whole, so I'm not writing M1 or M2 because M is constant. R I think given in the question, is it? Okay, it has been assumed to be air, so R can be calculated or it can be directly remembered since it is already given as air. So R can be calculated or remembered. So from this, when you calculate, you will get M as you will get M as 9.29 9.29 into 10 to the power minus 5 kg per second. Oh, sorry, this will be only kg. This is a closed cycle, na? This is a closed cycle, so it will be only kg. There is no mass flow. It will be kg. So you have got the mass. You have got the mass. We know the value of Cp. We know the value of T3. We know the value of T2. We can now calculate the heat added. We can calculate the heat added. If we calculate the heat added, we have already calculated the efficiency. We have already calculated the efficiency. So we can get the work of the cycle. We can get the work of the cycle. So work of the cycle will come as 0.089 kilojoule. I have already done the calculation. This work of the cycle will come as 0.089 kilojoule. Okay, please make a note of it that since we are considering the work of the cycle, we have to consider the mass that is in the cycle. Since we are considering the work of the cycle, we have to consider the mass that is running through the cycle. Okay, we cannot ignore the mass. We cannot ignore the mass. Yeah, the heat is added only between 2 to 3, na? What is efficiency? Efficiency is the net work divided by heat added. So heat is added only between 2 to 3. So efficiency into heat added. Simple. That will give you the total work. So now you have the total work, the stroke volume, that is the swept volume, that is basically 70 cc. 70 cubic centimeter. Just keep in mind the unit, just convert the unit. So you can get PM, that is the mean effective pressure, is equal to work of the cycle divided by the stroke volume. Keep in mind the units. So when you do that, you will get the final answer, that is PM, the mean effective pressure, is equal to 12.71 bar. 12.71 bar. Okay, this is the answer that you should be getting. Yeah, that is also acceptable. That is the same. It's your wish in which unit you want to give. In the question, in gate question, they will mention the unit. In the gate question, they will mention the unit. But it is up to, for this question, because this is just a practice question, it is your wish. You can give in kilopascal, you can give in pascal, you can give in bar. Unit is not going to change the answer. Unit is not going to change the answer. Okay. So I think this much is clear. This much is clear. So let's move on to the next question now. Okay, the next question is a psychometric question. Okay, so the question is coming in front of you. Right? Now, read it. This question is a long one. So read it. Take your time and read it. Okay, how V3 is calculated? Okay, let me come in front of you then. Okay, see, V3, how V3 was calculated. See, the expansion ratio was given in the question, right? The expansion ratio was given in the question. The expansion ratio, that is RE, this expansion ratio is basically this ratio, and the ratio of V4 divided by V3. This is the definition of the expansion ratio. That is V4 divided by V3. And of course, V4 is equal to V1. V4 is equal to V1. So V1 divided by V3. Okay. This was given as 1.6. As far as I remember, this was given as 1.6. So V1 is known. So V3 can be calculated from here. V3 can be calculated from here. I hope that is clear. I hope that is clear how V3 was calculated. Now come back to this question. Come back to this question. Read the question. It is a long one. Okay. Read the question. Let me read it with you. A stream of moisture, the mass flow rate is given with specific humidity. The specific humidity is given in kg per kg of dry air. Mixes with a stream of superheated vapor such that the specific humidity increases to 0.02 kg per kg of dry air. Okay. Then the mixture is passed through a cooling coil with a with a coil temperature of 27 degrees Celsius. That is, the coil has a temperature of 27 degrees Celsius, such that the humid air is cooled from 35 to 30 degree Celsius isobarically. Okay, so from 30 degrees Celsius, cooled from 35 to 30. Correct. It is cooled from 35 to 30 degrees Celsius. Okay, 35 to 30 degrees Celsius isobarically. If P sat at 30 degrees Celsius, so they have given some data. That is the saturation pressure at 30 degrees Celsius. The saturation pressure at 30 degrees Celsius is given as 4.2461 kilopascal. Correct. Calculate mass flow rate of superheated vapor, relative humidity of air exiting the coil, the efficiency and the bypass factor of coil. Plot the process on a psychometric diagram. If the initial temperature of air was 20 degrees Celsius, the initial temperature was 20 degrees Celsius, And we have to assume that the barometric pressure is 100 kilopascal. So the barometric pressure or the total pressure is 100 kilopascal, and that remains constant. And that remains constant. Okay. So see, this is the data. This is the data that they have given. This is the data represented on the board, that at 1 some air is entering at 20 degrees Celsius. Then as it is going forward, some superheated steam is mixing with it. Then it is going, it's coming at 2 with a temperature of 35 degrees Celsius. Then it is passing through a cooling coil and the temperature is dropping to 30 degrees Celsius. Okay, this is all the data that they have given. Okay, so now see how to do this question. Let me write down the given data as well. So they have given the mass flow rate. The initial mass flow rate is 10.1 kg per second. Specific humidity at 1 they have given as 0.01. W2 they have given as 0.02. Temperatures are represented. Okay, everything else is represented. Okay, so this is all the data they have given. This is all the data that they have given. Okay, now let's revise the concept of psychometry, or basically mixture of ideal gases. Let's revise it a small bit. Okay, so what we know is the mole fraction. Let's say the number of moles of any particular gas by the total number of moles, that is sigma n, is equal to the partial pressure of that gas divided by the total pressure. Correct? This much you know, I guess. This much you know. Okay. So now see. So the total pressure they have given, the total pressure remains the same. The total pressure 100 kilopascal, the atmospheric or the barometric pressure, this is a constant. This is a constant. So what that means that as long as the moles of any gas, the moles of water vapor is a constant, that is, if Nk is a constant, then this and this will also be a constant. Correct? As long as the moles are remaining constant, the moles are not changing, nothing here will change. Correct? Because Pt is a constant. If the number of moles do not change, that is, no water is added or removed from the air. If no water is added or removed from the air, then the moles of water will not change, the total moles will not change. So the pressure, the partial pressure of water vapor will also not change. I hope this much is clear. Is this much clear? That the total pressure 100 kilopascal, that is a constant. 100 kilopascal, that is a constant. So if the number of moles of the water vapor does not change, the number of moles of water vapor plus dry air does not change, as long as these two things are constant, the partial pressure of water vapor, the partial pressure of water vapor is also going to be a constant. Is also going to be a constant. I think this much is clear. Okay. Now let's proceed forward. This will be useful, but now let's proceed forward. Okay. So let's see how to do this question. But first, tell me one thing, one important thing. This m dot 1, the mass flow rate at 1, is this the mass flow rate of dry air or the mass flow rate of moist air? This mass flow rate, that is m dot 1, this mass flow that is entering at 1, is this the mass flow rate of dry air or the humid air? Tell me that. Is this the mass flow rate of the dry air or the humid air? Read the question again. Read the question. I'm bringing the question. So here's the here's the question. Yeah, a stream of moist air mass flow rate is given as 10.1 kg. A stream of moist air and mass flow rate is given as 10.1 kg. So basically 10.1 kg is the mass flow rate of the moist air. 10.1 kg is the mass flow rate of the moist air, not dry air, the moist air. So that means That 10.1 is because of the mass flow rate of the dry air plus the mass flow rate of the water vapor. Correct? The 10.1 is because of the mass flow rate of the dry air plus the mass flow rate of the water vapor. Okay? Clear up to this part? Clear up to this part? So let's see. So I can say that this 10.1, that is m dot 1, is because of the mass of the dry air at 1, the mass flow rate of dry air at 1, plus the mass flow rate of the water vapor. The mass flow rate of the water vapor. That is the mass flow rate of the H2O at 1. Correct? Correct up to this part? Now see, this mass flow rate, that is m dot H2O divided by m dot dA is basically what you call as specific humidity. Correct or not? This mass flow rate of the water, that is water vapor, divided by the mass flow of the dry air is what you call as the specific humidity. Correct? So if you need to know this, all you need to know is m dot 1 is equal to m dot dA plus W1 into m dot dA from this relation. Correct? Correct up to this point? So this is known 10.1. This is a variable, MDA is a variable, W1 is known, W1 is known. So from this, when you calculate, you will get the mass flow rate of the dry air. The mass flow rate of the dry air will come as, let's see, 10 kg per second. This is the m dot dA, 10 kg per second, and this is going to be a constant. The mass flow rate of the dry air is not going to change. The mass flow rate of the dry air is not going to change. So this is going to be a constant. This is going to be a constant throughout the process. The mass flow rate of the dry air is going to be a constant throughout the process. The mass flow rate of the water is definitely going to change. The mass flow rate of the water, humidity, that is going to change. Here it was less, after some water addition, that will be more. So this is a variable, the mass flow rate of the water is a variable, but this is going to stay the same. The mass flow rate of the dry air is going to stay the same. Okay? Yes, the mass flow rate of the dry air in any air conditioning application stays the same. Because what happens is, once the mass of dry air enters into your system, once the mass of the dry air enters in your system, you are not going to condensate any of the gases, correct? You are not going to liquefy the oxygen or the nitrogen or the argon or carbon dioxide. You are not going to liquefy any of the gases. So the mass of the gases, the mass of the dry gases that is coming in is always going to stay the same. The mass of the dry air, that is the dry gases that is going to come in your system, in your air conditioning system, is always going to stay the same. But the mass of humidity, that is the mass flow rate of the water vapor, that can be changed. You can condense the humidity from the air, you can add more humidity to the air. So the mass flow rate of the water vapor can change. The mass flow rate of the water vapor can change. The total mass flow rate, that is the mass flow rate of the moist air, can also change. But the mass flow rate of the dry air is not going to change. In any air conditioning application, the mass of the dry air is not going to change. I hope that is clear. Okay? So now see. So now they have given that the W2, specific humidity at 2. So what we can say is, let's see W2. So can we write the mass flow rate of the humidity, the mass flow rate of water vapor at 2 divided by the mass of dry air at 2 is equal to W2. Okay? Can I write this? That the mass flow rate of humidity at point 2 divided by the mass of dry air at point 2 is equal to W2. The mass of dA2 is the same as m of dA. This is not going to change. M dA2 is same as mdA. That is not going to change. W2 is known. W2 is known. So we can get from this data that the mass flow rate of the water vapor at point 2
is going to be 0.2 kg per second. 0.2 kg per second. I think this is clear. This much is clear. Okay. So now see. Now we are going to. So now basically what I am going to do is the mass of water vapor coming in plus the mass of water vapor coming in from superheated steam is equal to the mass of water vapor at point 2. Correct? That is mass of water vapor H2O at 1 plus the mass of water vapor from this part, that is superheated steam, is equal to the mass flow rate of water at 2. Correct? Correct this much? Any problem with this? So now see, this H2O at 1, this is basically W1 into m dot dA at 1 plus ms is equal to m dot H2O at 2. So this is known. Mass flow rate of water at point 2, this is known. Mass of dry air is known. Mass of dry air is known. Specific humidity at 1. Specific humidity at 1. This is also known, and this has been asked. This has been asked in the question. This has been asked in the question. So put the value, and what you will get is, that is ms, that is the mass flow rate of the superheated steam. Mass flow rate of the superheated steam. This is 0.1 kg per second. This equation is basically the conservation of mass of water. This equation is the conservation of mass of water. The mass of water coming from here plus the mass of water vapor coming from here is equal to the mass of water vapor at point 2. Okay? Understood this part? Understood this part? Understood this part? So we have the mass flow rate of the steam, that is the superheated steam, as 0.1 kg per second. This was the first part of your answer. This was the first part of your answer. Clear up to this? Clear up to this? Is it clear or should I repeat? Tell me, is it clear or should I repeat? Type. Is it clear or should I repeat the concept again? Yes for what? Clear or repeat? Type one of them. Clear or repeat? Repeat once. Okay. So see. This is basically the mass conservation of water. This is basically the mass conservation of water. The water coming from 1 plus the water because of this superheated steam is equal to the water at point 2. Correct? Mass conservation of water. The water at 1 plus the mass of water added due to superheated steam is equal to the mass of water at point 2. Okay? This much is clear? Now see. This is basically the formula. This is the formula for the specific humidity. That is the mass of water vapor divided by the mass of dry air. This is the formula for the specific humidity. Mass of water vapor divided by the mass of dry air. Okay. So now see. W2 is known. W2 is known. We have calculated the mass of dry air. That is going to stay the same. We have calculated the mass of dry air. That is going to be constant throughout the process. So MdA is known. That the mass of dry air is known. W2 is known. So we can get the mass flow rate of humidity at point 2. We can get the mass flow rate of humidity at point 2. So this is known. Correct up to this part? Correct up to this part? Now see. Similarly, in this relation, I can also say this, that at 1, the mass of water vapor at 1, divided by the mass of dry air is equal to the specific humidity at 1. The mass of water vapor at 1 divided by the dry air is equal to specific humidity at 1. So mass of dry air is known. W1 is given. So from this I can get the water vapor at 1. That is, this is basically W1 into MdA. This is basically W1 into MdA. Okay. As I have said, this is basically the conservation of water mass. This is the conservation of water mass. And the last part, that was the first part. This mass flow rate was basically the mass of dry air plus mass of water vapor. Mass of dry air plus mass of water vapor. Okay, so mass of dry air and the mass of water vapor, this can be written as W1 into MdA. W1 into MdA. Okay, this is the mass of water vapor at 1. So from this equation, when you solve, you have the value of M1. You know the value of W1. The only variable is MdA. So the mass of dry air will come as 10 kg per second. Okay, the mass flow rate of the dry air will come as 10 kg per second, and the mass of dry air is a constant for your air conditioning application. The mass of dry air is always a constant for your air conditioning application. Why? Because in any air conditioning application, in room air conditioning application, you are not going to condense the gases. You are not going to condense nitrogen. You are not going to turn nitrogen into a liquid. You are not going to turn oxygen into a liquid. So if the gases are not going to be condensed, if the gases are not going to turn into a fluid, then the gases that you have sucked in, once in your system, is going to stay in your system and finally come out of your system. Correct? The gases, the mass of gases that once you have sucked inside your system is going to stay in the form of gases and will come out also. So the mass of dry air is always a constant. The mass of dry air is always a constant. Clear? Clear? Type it down. Is it clear? Or any doubt? Clear or any doubt? Okay, so it is clear. So let's proceed forward now. Let's proceed forward. So now see, from 2 to 3 is basically isobaric cooling. Okay, it is given in the question also. You can read in the question also. I am putting up the question now. See, then the mixture is passed through a cooling coil from the third line. Then the mixture is passed through a cooling coil with a temperature of 27 degrees Celsius such that the humid air is cooled from 35 degree to 30 degree isobarically. Okay, so basically this cooling that occurs in the cooling coil is basically isobaric cooling. Okay, this is basically isobaric cooling. Okay, so if this is isobaric cooling, if the pressure remains constant, that means that the total pressure and the partial pressure of water vapor both will be a constant. Correct? Correct or not? The partial pressure and the total pressure, both of this pressure is going to be a constant since the cooling is isobaric. Okay, so this is going to be a constant and this is also going to be a constant. So what that means is the vapor pressure at 2 is the same as the vapor pressure at 1. Sorry, is the same as the vapor pressure at 3. The pressure of the water vapor at 2 is the same as the water vapor pressure at 3 because the water vapor pressure is going to be a constant. Correct? Correct up to this part? Correct up to this part? Similarly, the pressure of the moist air or the total pressure is also going to be a constant. The total pressure is also going to be a constant. The total pressure is also going to be a constant. Correct? The total pressure is also going to be a constant. Okay? And from 2 to 3, no water has been added or removed. From 2 to 3, no water has been added or removed. That is, N of H2O, the moles of H2O is also a constant. From 2 to 3, no water has been added or removed. So the moles of H2O is also a constant. So this is a constant, this is a constant, this is a constant. So that means the number of moles, that is total number of moles, is also going to be a constant. Correct? This is a constant, this is a constant, this is a constant. So this will also be a constant. So what I can say is that W2 is the same as W3. The specific humidity, or I should say as the mass of water vapor at 2 divided by the mass of dry air at 2 is the same as the mass of water vapor at 3 divided by the mass of dry air at 3. This is always a constant, and since no water has been added or removed, so this is also going to be a constant. Okay, so the specific humidity is also going to be a constant. Correct? Everything is going to be a constant apart from the temperature. Everything is going to be a constant apart from the temperature. Clear up to this part? Clear up to this part? Because of isobaric cooling, the pressure is going to be a constant. Since no mass is added, since no water vapor mass has been added, so this mass of water vapor is also going to be a constant. Mass of water vapor is also going to be a constant. Mass of dry air is always a constant, and this thing is basically W2 and this thing is basically W3. So specific humidity is also going to be a constant. The specific humidity is also going to be a constant. Okay, so in the question, had they asked something like this? Let me see. Calculate mass for it. Relative humidity of air exiting the coil. Okay, so we need to know the relative humidity. That is, we need to know phi 3. We need to know phi 3. Okay, so what is phi 3? Phi 3 is nothing but PV3 by P saturation at 30 degrees Celsius. Or I should write it P saturation at 3, and both will be at 30 degrees Celsius at the same temperature. Okay, or just make it simple, P saturation at 30 degrees Celsius, because here the temperature is 30 degrees Celsius. At this point the temperature is 30 degrees Celsius, so phi 3 is basically PV3 by P saturation at 30 degrees Celsius. Okay, yeah, psychometry appears to be new and confusing to people, but don't worry, psychometry is actually very simple. You just need to revise this once more, but psychometry is actually very simple. Okay, this is the definition of relative humidity. This is the definition of relative humidity, that PV3 divided by P saturation at the same temperature. PV divided by P saturation at the same temperature. Okay, so now I need to know PV3 because P saturation is already known. I need to know PV3 because P saturation at 30 degrees Celsius is already given. Okay, so PV3 is equal to PV2. PV3 is equal to PV2. So let's see, can I find out PV2? Can I find out PV2? So let's see that. So I know that W2 is nothing but 0.622 into PV2 divided by PT minus PV or PV2. Are you familiar with this relationship? Tell me that. Narendra Agrawal, tell me, are you familiar with this formula? Are you familiar with this formula? Narendra Agrawal, are you familiar with this formula? The relationship between specific humidity and the partial pressure? Okay, so this formula I'm using, this is the formula that I'm using. So from this we can calculate PT is known, PT is known, W2 is known, W2 is known. So from this I can get PV2 will come to me as 3.11 kilopascal. 3.11 kilopascal. Okay, and PV2 is equal to PV3. PV2 is equal to PV3. So now I have PV2. So now I can substitute. This PV2 is basically PV3. So when you do the substitution, this relative humidity will come as 73.5 0.37 percentage. This relative humidity will come as 73.37 percentage. Okay, 73.37%. Okay, so this is the relative humidity at the exit. This is the relative humidity at the exit. Now they are asking the bypass factor and the efficiency of the coil. The bypass factor and the efficiency of the coil. So let's do that also. The efficiency of the coil, that is neta coil, is defined as the actual temperature drop divided by the maximum possible temperature drop. Okay, efficiency of the coil is the actual temperature drop. The actual temperature drop is from 35 to 30 degrees Celsius. So from 35 to 30 degrees Celsius, we are taking the difference, no need to convert it into Kelvin. So the actual temperature drop is from 35 to 30 degrees Celsius. But what could be the maximum temperature drop? What could be the maximum temperature drop? The maximum temperature drop could be 35 minus 27. That is, if the air could be cooled to the temperature of the cooling coil, if the air at 35 degrees Celsius could be cooled to the temperature of the cooling coil, then that is the maximum possible cooling that is achievable. Because the air cannot be cooled below 27, because that is the temperature of the cooling coil. The air cannot be cooled below 27. So 35 to 27 is the maximum cooling achievable, and the actual cooling that we are achieving is 35 to 30. 35 to 30 is the actual cooling, and the maximum cooling is 35 to 27. Okay, so the efficiency of the coil will come as, the efficiency of the coil will be 62.5%. 0.5%. And the bypass factor, there is a relation basically, that bypass factor of the coil is basically 1 minus the efficiency of the coil. The bypass factor of the coil is basically 1 minus efficiency of the coil. So this will come as 37.5%. 37.5%. Okay, clear up to this part? This is all the data related question that they have given. Now we just need to plot the diagram. So let's do that. Let's just plot the diagram. Let me draw it here. So a psychometric chart looks something like this. Let's mention the pressure as 100 kPa. This is dry bulb temperature, and this is the specific humidity. Okay, so initially the air was at 20 degrees Celsius and the temperature is rising. Okay, so initially the mixture was at 20 degrees Celsius, the moisture, and the temperature is rising. So if my initial point is here, then from 1 to 2, let's say this point is 1, so 2 would be on the right hand side of 1, because the temperature is rising, so 2 would be on the right hand side of 1. Another interesting point is that the specific humidity is increasing. From 1 to 2, the specific humidity is also increasing. So 1 to 2 will go something like this. This is 0.2. Okay, this is 0.2. The specific humidity is also increasing and the temperature is also increasing. Correct? The specific humidity from 1 to 2 is increasing, and the temperature, dry bulb temperature, is also increasing. Okay, then from 2 to 3, there is just simple cooling, that is 35 to 30 degrees Celsius. Basically from 2 to 3 the temperature is cooled, the dry bulb temperature will come back, but the humidity is not changing. That is W2 is equal to W3. Correct? The specific humidity is not changing. So this will be something like this. So this is 0.3. This is zero point 0.3. Let's say 0.3 was at, this is 30 degrees Celsius, and 0.1 was at 20 degrees Celsius, and 0.2 is at 35. So this is 35 degrees Celsius. Okay, every other data is known. You can plot them if you want. Let me do it for you. The W1 was given as 0.01, and W2 will be 0.02. That's the plot. That's the plot of the process on the psychometric dia. Oh, sorry, on the psychometric diagram. That is the plot. 1 to 2 and from 2 to 3. That is the plot on the psychometric dia. Okay, clear up to this? Clear up to this? Inclined as specific humidity increases. Yes, inclined because the specific humidity is increasing. Okay, so that's all. That was all the question that I had intended for you to solve and see. So, any other doubt? Now we are going to keep a small doubt clearing session. We are going to keep a small doubt clearing session. So tell me, do you have any doubts? Okay, do one thing. Take a small break now. Take a small break. See if you have any doubt, and then we will come back. Okay? Take a small break. See if you have any doubt, and then we will come back. The break will be of precise 8 minutes. I have a stopwatch and I will keep count. The break will be of precise 8 minutes. Okay? So let's start the break now. So, any doubts? Yeah, velocity triangle analysis and compressor. Okay, so let me tell you the thing about velocity triangle is you learn about velocity. Are you there, Narendra Agarwal? Tell me that first. Are you there? Mr. Narendra Agarwal, are you there? Okay, so let me tell you. The thing with velocity triangle is you learn the concept in fluid mechanics. Okay, the velocity vector diagram, the velocity triangle, you learn them in fluid mechanics. And once you have learned them, once you have learned the velocity diagram, they are the same for turbines, be it hydraulic turbine or steam turbine. The concept of velocity diagram, velocity triangle stays the same. Be it pump, be it compressor. The concept of the velocity triangles will always be the same. Okay, the concept of the velocity triangles, be it for centrifugal pump, compressors, turbine, steam turbine, water turbine, will always stay the same. They are not going to change. So learn it once, learn it well, then you can apply it everywhere. Now, as far as GATE syllabus is concerned, pump, that is fluid pumps, and turbine, fluid turbines, hydraulic pump, they can come, they have come. Velocity triangles on based on hydraulic turbines and hydraulic pump, they have come. As far as GATE syllabus is concerned, I have not seen steam turbine and compressors. I have not seen gas compressors and steam turbine question velocity diagram. Yeah, but in IES, in the paper of IES, there are questions based on the velocity diagram in steam turbine. But the concept is the same as the velocity diagram in hydraulic turbine. Okay, so no need to worry about that. Only in IES you can encounter steam turbine velocity diagram. In GATE, you are only going to counter centrifugal pumps and hydraulic turbines, but about this compressor, they have never come. Okay, for calculating entropy in those cases, that the wall, assume one side of the wall as a temperature source and the other as a temperature sink. How to solve this? Let me show you. If there is a wall like this, let's say this is T high, this is T low. Assume this as a thermal energy reservoir and assume this as a thermal energy reservoir. So let's say Q is coming. So the entropy change of the universe, del S universe, this is basically TH is losing some heat. So minus Q divided by TH, and TL is gaining some heat. So plus Q divided by TL. Sorry, TL. This is your entropy generation of the universe or entropy generation, del S gen. This is how you solve it. Consider each of the side as a TER, thermal energy reservoir. That's how you solve it. Of course, the heat is going to be conserved. The heat that is traveling from this side will reach this side. No heat loss. I am assuming there is no heat loss. The heat that is traveling from this side will reach this side. Okay, so that is how you solve the question. It's a good question, no doubt about that. If surrounding temperature is also given, see, if the surrounding temperature is also given, then it means that after this point there is also heat going to the surrounding. Correct? If there is surrounding temperature, then that means that from this point the heat is also going to the surrounding. So that you can consider. If this wall is completely adiabatic, if this wall is completely adiabatic and there is no heat loss to the surrounding, that means that they are giving T naught, that is the temperature of the surrounding, just so that you can calculate I, because I is T ambient into del S universe. Even if there is no heat loss from this wall to the surrounding, even if there is no heat loss from this wall to the surrounding, even then there will be a del S universe. There will be a del S universe, and because of that, if the surrounding temperature is given, there will be a irreversibility associated with the process. That is why they give the surrounding temperature, when they want you to calculate the irreversibility associated with the process. And if the wall is not adiabatic, then you have to see the heat is that is getting lost to the ambient. If the wall is not adiabatic, then some heat will be also lost to the ambient. So there will be another term which will be plus Q divided by TA. Plus Q divided by TA, because the heat is also gained by the ambient. If the wall is not adiabatic, if there is some heat loss. Any other? Any other doubt? Work done by stirrer is always negative in cylinder piston arrangement. Yes. So see, the paddle work is usually given. Unless it is stated in the question, unless it is stated so in the question, we are always going to assume that the stirrer work is negative. That is, the work is given to the system. Okay, because that is how the stirrer function. That there is a stirrer and you move it from the outside. So stirrer work is always taken as negative. But if it is given in the question that it is not negative and somehow the stirrer is rotated because of the fluid, in that particular case we have to take it as positive. Otherwise, unless mentioned, that stirrer work is always coming into the system and hence negative. Any other doubts? See, if the piston is moving up, then some work is positive. If the piston is moving up and there is an increase in volume, then that means some work is also positive. But that cannot mean that the work done by the stirrer is not negative. Na? What is happening, basically what happens is, see here. Suppose this is a system, I can supply a negative work by a stirrer. Let's say a stirrer is there which is supplying a negative work. I can also supply negative work by some electric current. Let's say some 10 kilowatt. I can also supply some electric current. It will be also treated as negative work because the work is going into the system. And after that, it may happen that the piston, there is a rise. Because of all of this, there is a piston rise. Okay, so the work done by the piston is positive and the work done by stirrer and this is taken as negative. So the net work will be the sum of all this work. Degree of reaction calculation from velocity triangles diagram. That is the doubt for fluid mechanics. That is not a doubt for thermodynamics. That is a formula and doubt for fluid mechanics. So currently we are only solving about thermodynamics. But DOR calculation is basically just a formula, nothing more. The DOR, the degree of reaction, is basically a formula. You just have to calculate the various velocities. You just need to calculate the various velocities. That's it. No, electric current is always treated as work. If electric current is supplied, electric energy is supplied into the system, it is always treated as work. Understand that point. If there is electric current supplied into the system, that is always treated as work. Electricity is always treated as a work, not heat transfer. Okay. Now it may happen that because of work there is a rise in temperature. Consider an adiabatic process. Consider an adiabatic process. Q is equal to 0. So when there will be work transfer into it, when there will be work transfer into an adiabatic process, then the temperature will rise automatically. Correct? Q is 0. So when there is a work transfer, that is negative W, so U will rise automatically. So work can increase the temperature. It is not right to say that only heat addition can increase the temperature. Even work addition can also increase the temperature. An electric heater or electric energy is treated as a work. It may so happen that the temperature of the system is increasing, but that temperature is increasing because of the addition of the electric work. So electricity is always treated as work and never as heat. Keep that in mind. Electric current, if coming into the system, it is treated as work. Okay, you are asking for adiabatic process? Yes. If adiabatic process is there, if there is adiabatic process, so heat transfer will always be zero. There will be no heat transfer. So any work that is put into the system will turn into increase of internal energy. Turn into increase of internal energy. It may so happen that by increase of internal energy, I can mean the increase in kinetic energy, potential energy, chemical energy. All this form can also be acceptable. But if these forms are, if this that is kinetic energy, potential energy, chemical energy, if all of them are neglected, then that means that the work done on an adiabatic system will increase the temperature. Yes, the temperature can rise even if there is no heat transfer. The temperature can rise and fall even without heat transfer. Energy is maximum available energy. Exergy. Exergy is basically the available energy. Exergy is basically the available energy. And available energy is the energy that you can convert into work. The maximum amount of energy that you can convert into work is known as available energy or exergy. Change of reversibility. See, if the process is completely reversible, if the process is completely reversible, then available energy is not going to be destroyed. If the process is completely reversible, the available energy coming in is equal to available energy going out, plus if there is some internal generation also, but in steady state, we do not consider any change of the available energy within the system. Okay, so if a reversible system is there, there will be no loss of available energy, that is I will be zero. But if the system is irreversible, the exergy or the available energy will be destroyed. What I mean is the available energy will be converted into unavailable energy. The total energy is going to stay the same, but the available energy is going to convert into non-available energy. And hence we say exergy or the available energy is destroyed for an irreversible process. You mean dead state? What kind of energy? Energy is not zero, but available energy is zero. Exergy is zero. Because at dead state, what we mean is the system and the ambient are at the same state. There is no temperature difference, no pressure difference, no velocity difference. So unless there is a difference between the system and the surrounding, no energy can be extracted from the system. So you have no available energy. You have no available energy when the system and surrounding are at the same temperature or dead state. But that does not mean that the energy of the system is zero. The system can have some energy. The system can have some potential energy, kinetic energy, or even if they are not there, then some internal thermal energy because of intermolecular energy. But that energy cannot be extracted. That energy cannot be extracted because the system and the surrounding are at equilibrium. That is what dead state means. That the system does not have a zero energy, but no energy can be extracted from the system. That is what we call as dead state. Any other doubts? Yes, any other doubt? Then post it in the comments. When you remember them, post them in the comments. Okay? So let's end the session now. Hope you have liked this session. Please share it with your friends and juniors. Most important, with your friends and juniors, particularly your juniors. Be a good senior to your juniors. Share with your juniors so that they can also learn from because of from first year and second year, from third year, just for the class syllabus, just so that the thermodynamics is more clear to them from the class or semester point of view. So share it with your friends and your juniors. Most important, with your juniors. Be a good senior. Everybody can be a good friend, but you should also be a good junior. Sorry, senior. Okay? And thank you. Thank you for attending this session. Thank you for attending this session. Okay, so let's end it here. How can I say the level of thermo in this year? I haven't seen the paper yet, na. Even I haven't seen the paper yet. But some question will be easy. If I have to guess, then I will say that some question will be easy. Some might be a bit difficult. Not much. A bit of your thinking will be required, but most should be easy. And the question that you have learned from this concepts, from this video and the previous video, they should be ample. They should be ample to give you the basic idea of what kind of question they can ask in GATE. Okay. Thank you for all your appreciation and all your support. That is the best gift for us, best New Year gifts. So, hopefully, you have liked this session and found it useful. Please share and subscribe. And also, ask your doubt in the comment. Don't do half the work. Ask your doubt in the comment and press the bell icon for your notification. Okay? So, bye bye. Let's end this session here now.